talks. It is my great honor to introduce to you our first speaker of this session, Professor Antoine Henrot from University of Lorraine, Nancy. Professor Henrot is a recipient of the Frontiers of Science Award for his work on maximization of the second non-trivial Neumann eigenvalue. And in this talk, he'll give a review on the award-winning work along with some more recent results. So now, let's welcome Professor Henrot.
Thank you. So the introduction was perfect. I have nothing to add. So thank you for the organizer to give me the opportunity to talk here. So as you said, I am going to report first on my work with Dorin about the maximization of mu2. I will fix the notation in a moment. And also with work with Marco Michetti, who was a former PhD student, Antoine Lemenant and Ilaria Lucardesi, who were colleagues in Nancy. Now Ilaria is moved to Pisa. Everything is about Neumann eigenvalues. So Neumann eigenvalues are the numbers mu such that this following PDE has a non-trivial solution. So it's the eigenvalue of the Laplace operator. I am in the Euclidean case, meaning that my omega is a bounded domain in Rn. It's not a manifold. And what we call the Neumann boundary condition is just we are dealing with function whose normal derivative is 0 on the boundary. And my notations, so I will fix it here, consist in writing, so the Julian is 0 on the boundary. And I choose to note the trivial eigenvalue. I tell it trivial because it is equal to 0, which correspond to a constant eigenfunction I denoted by mu0. So this is the first eigenvalue, but my numbering is telling that it is 0. And then the first eigenvalue I am interested in is mu1. Note that mu1 can also be 0, because if your domain is disconnected, you will have a double 0 eigenvalue, and then mu2, and etc. So we have a sequence of eigenvalues. The spectrum is discrete, it goes to plus infinity. And probably you know, but there are very few domains in Rn, or even in the plane, for which you are able to compute exactly this sequence of eigenvalues. Basically, there are rectangles, if I am in the plane, rectangles, disks, circular sector, equilateral triangle, isocele rectangle triangle, and that's it. So it's really important if you want to deal with these quantities to have bounds for these eigenvalues in terms of simpler quantity, and what I call simpler quantities, geometric quantities. So I will introduce the area or the volume of the domain, the perimeter of the domain or the surface area in higher dimension, and the diameter of the domain. And my aim is to have some idea of the possible values taken by this mu k in terms of these geometric quantities, right? So an important tool when you deal with eigenvalue is their variational characterization. So they are characterized as minimum of the Rayleigh quotient. This quantity, this ratio, is named the Rayleigh quotient because it was introduced by Lord Rayleigh. And for mu1, you have to minimize this Rayleigh quotient, taking into account that you have to be orthogonal to the first eigenfunction, which was a constant. So you have to have a mean value 0, and you get mu1. If you do that, and the minimum is achieved, and the minimizer is precisely the first eigenfunction. That's the first non-trivial eigenfunction that I denote by u1. Since I am interested in mu2 in this talk, I also write the variational formulation for mu2. It is the same, but now you have to be orthogonal to the first trivial and the first non-trivial eigenfunction. So you have these two orthogonality conditions to satisfy when you minimize the Rayleigh quotient. And of course, you can go on, define a similar formula for mu k. And if you do not want to involve the previous eigenfunction, you have also min-max formula, which is well known. Mu k can be obtained by this min-max formula where the minimum is taken over all the subspace of dimension k, which are already orthogonal to constants, which can be convenient if you do not want to involve the previous eigenfunction. Okay, so as I said, my aim in this talk is to get bounds, if possible, optimal bounds in terms of these geometric quantities, volume, perimeter, diameter. It means that I am actually looking at shape optimization problem in the sense that I want to minimize or to maximize an eigenvalue, a given eigenvalue mu k, by considering all domains with a volume given, or a perimeter given, or a diameter given. If I want the optimal bound, I am obliged to do that. I'm obliged to find at least the value of this shape optimization problem. So of course I will not be successful in all cases, but I will tell you what I can do. An important property is that when you inflate your domain by a factor t, when you consider t omega instead of omega, the eigenvalue is reduced by t squared, is divided by t squared. So if you want to get rid of the constraint, which is interesting in particular from a numerical point of view or something like that, you just have to scale the eigenvalue in order to have a scale invariant quantity. For example, if I am in 2D, in the plane, the scale invariant quantity will be the area times the eigenvalue, or the perimeter square times the eigenvalue, or the diameter square times the eigenvalue, which does not depend on the scaling. And now I can try to minimize or maximize these quantities without constraint. This is equivalent. Okay. So let's start with minimization or maximization of the eigenvalues with the volume constraint. So there are two problems, minimization or maximization, and the infimum problem is trivial. Actually, the infimum of mu k, if I fix the volume of the domain, is 0, because as I said, you can just take a union of balls, or balls of anything. So you just take k plus 1 balls. You manage in order that the volume constraint is satisfied. And of course, since it is a disconnected domain, the eigenvalue will be 0 repeated k times, because for each ball you can put a constant on this ball, 0 on the other balls, and you have a family of k plus 1 independent function for which the eigenvalue is 0. So the dimension of the space is precisely k plus 1, and uk is 0. So the infimum problem is not interesting here. This is a maximum problem which is interesting, which is an old one, which has been solved first by Zege, but only in the plane and among simply connected domains. So Zege used conformal maps to do that. Conformal maps is a convenient tool because you know that in the Rayleigh quotient, the numerator involves the Dirichlet energy, and when you do conformal maps, this Dirichlet energy is unchanged. So it's very convenient. And it has been generalized by Weinberger 2 years later in any dimension without any restriction on the topology. He proved that when you maximize mu1 with a volume constraint, this is a ball, which is a maximizer. So this is a counterpart of the famous Faber-Krahn inequality for lambda 1 for the Dirichlet eigenvalue. You get the same solution. The ball both minimize lambda 1, the first Dirichlet eigenvalue, and maximize mu1, the first Neumann eigenvalue. And of course, there are many problems in spectral geometry where the ball is expected to be the solution. Okay, so just an idea of the way Weinberger proceeded, because for mu2, we will be inspired by the proof by Weinberger. So what Weinberger did, for the ball in Rn, actually mu1 is of multiplicity n. You have n eigenvalue corresponding to mu1, which are given by a quantity like that. I mean that you have a radial part involving the Bessel function, and you have the coordinates. And that you get the n eigenvalue associated to mu1. So you have some Bessel function, some radial part involved in the Bessel function. Outside the ball of radius capital R, you extend it by a constant. So now you have a function which is defined on the whole space. And you define that way possible test function for your variational characterization. But you remember, in my Rayleigh quotient, I have to deal with test functions which are orthogonal to constants, which has mean value 0. So you have to work in order to be able to find a particular point, a particular origin, in such a way that the test function you have built are precisely orthogonal to the constant. And this is using the topological argument. This is using a Brouwer type theorem, fixed point theorem. You can prove that indeed there exists a point for which, when the origin is chosen at that point, these n equations, because you have n equations here, are satisfied. As soon as you have this property, you plug into the Rayleigh quotient this function uk, you play with the Bessel functions, you play with the properties of Bessel function, and you use a mass transplantation argument, because you have your domain, original domain, and you have a ball of same volume. I'm not much better than you. And you put what is outside inside. You have the same volume which is outside and inside, and you prove that in the Rayleigh quotient. Doing that, you increase your Rayleigh quotient. And when you are on the ball, precisely you have the eigenvalue of the ball. So at the end, you get that mu k of omega, your original omega, is less than mu k of the ball, using this transplantation argument. Okay, so the proof is not simple, but it is straightforward. I mean, it's natural to do that way. So with Dorin, we were interested in the same problem for mu2, so the next eigenvalue. And we wanted to maximize mu2 among domain with a fixed volume, right? And our proof is, our result is the following. The domain which maximizes mu2 is the union of two balls now. And here also, this is a counterpart of what happens in the Dirichlet case. But in the Dirichlet case, it's much simpler to prove. In the Dirichlet case, I told you that the minimizer of lambda 1 is one ball. This is Haber-Krahn inequality. And the minimizer of lambda 2 is the union of two balls. And it is very easy to get. You just think to the nodal domain of the second eigenvalue. You split into two subdomains. You use Haber-Krahn for each subdomain. So it's a two lines proof, basically. Here, as you will see, this is much more complicated. Let me mention that this result has already, like Zege did in the case of mu1, in the case of the simply connected planar domains, you can use conformal maps, and you can use very complicated topological argument, foliation, and so on, already used by Nadirashvili in some other works, to obtain the same result, that the fact that the union of two disks maximize mu2 for simply connected domain in the plane. So finally, what we did is the same as Weinberger. We generalized this 2D result to n dimension, but of course the proof by Giroir, Nadirashvili, Polterovich, using conformal maps cannot be used, cannot be generalized to any dimension. So how do we proceed? Before that, let me just make a small aparté on the Polya conjecture, on one of the Polya conjectures. There are many Polya conjectures. It's well known that when you are interested in the behavior of eigenvalue when k is large, you have a Weil asymptotic. Precisely this one. When k goes to plus infinity, the eigenvalue mu k is equivalent to this Weil asymptotic. Basically, by the way, this is exactly the same asymptotic for Dirichlet eigenvalue. Okay, and Polya said, oh, probably this asymptotic is not only an asymptotic, but it's a universal upper bound for the eigenvalue. Probably mu k is always less than the Weil asymptotic. And moreover, he was able to prove it for planar Taylin domains. You know what is Taylin domain, quadrilaterals, any triangle, and so on. But not necessarily convex, actually, in his proof. It doesn't need to be convex. Okay, but this conjecture is completely open now for general domains. It remains a mystery. Is it true? So it seems to be true, but finally we are able to prove this inequality only in very specific cases. And actually, it could be a motivation to try to maximize mu k with a volume constraint, or to maximize the volume with a good power time mu k, because if you are able to maximize it and compute the maximal value, you will be able to prove Polya conjecture just by comparison with the maximum value you get with this asymptotic. So it's precisely what we have done finally for k equals 2. So for k equals 1, it's a consequence of Weinberger. And for k equals 2, it's a consequence of our result. Because for k equals 2, I have two balls. I am able to compute the mu2 of two balls. It involves Bessel zeros. And I am able to find a value which is less than this one. So Polya conjecture is proved for k equals 2. I will come back. So no, the answer is no. We can think, okay, one ball from mu1, two balls from mu2, maybe three balls. But the answer is no. It is certainly not three balls. So we have candidates. Actually, even existence of a maximizing domain is not known for mu k. So we have numerical candidates, but not existent. Okay, so how can we prove our result about mu2? So I recall that the variational characterization of mu2 tells you that mu2 can be obtained as the minimum of the Rayleigh quotient among function u, which has to be orthogonal to constants, and to u1, u1 being the first eigenfunction, right? And so we would like to follow the same idea as Weinberger by introducing convenient test functions. So now our test function will depend on 2 points, because you have in mind that at the end we would like to have two balls as the optimal domain. So we introduce two points A and B, and we build possible test function inspired by the one by Weinberger. We have to pay attention to what happens when you are closer from A or closer from B. So we have to introduce the mediatrix, and to define my test function in a different way when I'm here and when I am here. So I skip details. And obviously, the main difficulty now is to be able. So we have good candidate for the test function. We denote it by UKAB, candidate to be test function. But obviously, the main difficulty is to be convinced that we can choose my A and B in such a way that the 2n relation are satisfied. So the number of degrees of freedom is 2n, because you have 2 points in Rn. And the number equation is also 2n, because you have to satisfy this orthogonality condition, right? Okay, so the first one seems tractable, because you just have to have mean value 0, so okay. But the second one, you have absolutely no idea of what u1 is, because it is the first eigenfunction of omega. So this is obviously the main point. So we need to use some theoretical argument to be able to prove that we can find 2 point A, B, such that these two M relations are satisfied. And this theoretical argument is just a topological degree. So I recall that we want to find 2 point A, B in Rn, such that these two N equations are satisfied. And the topological degree is a very convenient tool when you want to prove that something has a zero. When I was a student, a professor of me tell me, okay, when you are in 1D and you want to prove that a function has a zero, you just use the mean value, no, the mean value theorem. It's negative somewhere, positive. When you're in 2D, maybe use an index. When you are in higher dimension, use a degree. Okay, so I follow the advice. So what we do is first we fix the first coordinate, and you make an homotopy of the second one by choosing a specific ball. So of course I will skip many details, technical details. This homotopy, you see that in the second term I do not put U1. U1 remains only here. And to use the topological degree, we need to choose a box. Here it will be a big box, in such a way that when you travel into the homotopy, no roots will cross the boundary of the box. So topological degree is an integer which varies continuously when t varies. So if you do not cross the boundary of the box, this integer will remain the same. And the topological degree of f will be, which f corresponds to f0 here, where t equals 0, will be the same as the topological degree of f1, where this quantity has disappeared, and this is the quantity I am in trouble with. So, of course, this is the technical part. To prove that no zero crosses the boundary of the box, it requires much work. When you have done that, finally, you have transformed the second part into this simpler part. You do the same with the first part in order not to deal with omega itself. So you replace the first part by this homotopy. You do the same for another ball. And at the end, when t equal to 1, you are led to this much simpler function, which depends only on two balls. Obviously, you have to work with the test function you have defined at the beginning. And for this much simpler function, since my topological degree argument applies, I know that the topological degree of this function is the same as the topological degree of my initial function capital F. So it remains to compute it. But now you have two balls. You have two more or less simple functions. You can determine the zeros, determine the sign of the Jacobian, because the topological degree in the smooth case is the sum of the sign of the Jacobians at all zeros of my function, and prove that it is not zero. And if it is not zero here, it is not zero at the beginning, so my function f has zeros. So exists a, b, such that f of a, b is equal to 0. What is remarkable in this proof that actually it seems, and it is true, that it does not depend on U1. At some point, we use one property of U1, which is it is of mean value 0. But it is the only property we use. So finally, this property holds true for any function U1. It is not necessarily the eigenfunction of something, right? Okay. So let me move to the other geometric constraints, first with the diameter constraint. So I want to do the same. I want to minimize or maximize eigenvalues. Now, any eigenvalue, you can not only mu2, with a constraint on the diameter. Or as I said, it is equivalent to consider the scale invariant quantity diameter squared times uk, and I want to minimize it or maximize it. For the same reason, which is the same picture, if I fix the diameter and I minimize, the infimum will be 0 because here I have my disconnected series of balls and the diameter is fixed and mu k is 0. So the infimum is 0. The supremum is plus infinity, which is much less obvious to see. So let's fix, for example, the diameter to be 1. And it turns out that we can make an explicit computation with something which looks like this. So with a curve which is an exponential function, for which we are able to solve a 1D problem that we are going to encounter in a minute, and prove that in that case, if this is my omega epsilon, because I have to move this exponential to look like some peak which is thinner and thinner. So we are able to prove that mu1 of this goes to plus infinity. So proving that mu k also, and the fact that the supremum is plus infinity comes from such an example. So we can say if we do not want to add a supplementary constraint, the problem is not interesting at all. So as we did in shape optimization in that case, we say, okay, let's just do work with the convex domain, because for convex domain, we have no these counterexamples. So I will consider now convex domains. And I want to minimize or maximize these quantities, but adding the convexity, right? And as you will see, now the problem is much better posed. Alors, let's start with the supremum. What is remarkable is for the supremum of this quantity among, so I do it in the plane, but I can do it in the space in general. I will just give an information about it. But to explain, I think it's better to do it in the plane. So I want to consider the supremum of this quantity, diameter squared and mu k, among planar convex domains. So actually, we recover a result by Kruger that we were not aware, as often. Kishelka trova, Kishelka ritrova, the Georgie said. Which is an explicit bound. So you see what is remarkable is that we get an explicit, the explicit optimal bound for diameter square mu k. So this bound involves pi, nice, and G01, which is the first zero of the Bessel function G0 in the plane. And why is it, so it's a strict inequality, and why is it sharp? Because it is attained when you consider a sequence of collapsing domains. So in the case of mu1, this is a sequence of isocell triangle, and in the case of mu k, this is a sequence of collapsing trapezoid. So I mean collapsing, I mean that this goes to 0. An explicit trapezoid, not any trapezoid, with a quantity which is well defined. So when you want to deal with a higher dimension problem, it is more or less the same idea. It's even simpler in some cases. In particular, in the upper bound, you have not the pi coming into the game. You have just the zeros of a specific Bessel function. So let me explain how we get this. So first of all, so the diameter is fixed. So let's say that this is the diameter of my domain. First of all, we introduce what we call, so I make the explanation in 2D. So the diameter is being 0, 1, so segment 0, 1. So for any x in 0, 1, I introduce h of x, which is this. So we call it a profile function. I don't know if it has a name, another name in convex geometry. And of course, in higher dimension, you will do the same, but now it is a measure of the intersection of your convex domain with the hyperplane, which start at x. Okay, and we just choose a one-dimensional test function in my array recursion. So I consider a function v of x, not depending on y. Okay, and I compute the Rayleigh quotient for this function v of x. Of course, this is the reason why the profile will come out. When you integrate in y, you have just h of x, which comes out. So finally, my Rayleigh quotient of this function v is nothing else than the integral of v prime squared times the profile in the numerator, v squared times the profile in the denominator. And you are interested in minimizing, maximizing, you use the usual min-max formula. Now, this quantity, but it turns out that it is an eigenvalue of a Sturm-Liouville problem. Now you are in 1D, and you are interested in a Sturm-Liouville problem, which is the one for which you have this density, this weight. This is exactly this Sturm-Liouville problem where H appears both instead the operator and the lower term. You have Neumann boundary condition. So you have to pay attention because, as you can see, my H can vanish. On my picture, my function H is 0 here and here. So my problem is not uniformly elliptic. So you have to work a little bit in order to prove that this problem is well posed. In 2D, it's not difficult because in 2D, by Brun-Minkowski, H will be concave. In ND, always by Brun-Minkowski, this is the power of H is concave. So in ND, it's not clear whether this problem is well posed. When you have a concave function H, even if it vanishes at the extremities, you can write down explicitly the kernel, and you can prove that the problem, the eigenvalue problem is well posed. When it is a power of H which is concave, it's not clear because the kernel is not integrable, so you have not an Hilbert operator in L2, so it's more difficult. And so what is important, so you see that my previous comparison, my equality which is there, since I have chosen a specific function, you will get the fact that the mu k of omega will be less than the mu k of h. So I call mu k of h the kth eigenvalue of this term. You have an inequality between. And it turns out that inequality, actually, if you take a sequence of collapsing domain with a specific h, the inequality gives you an equality in terms of the supremum. So in the sense that for any h, I can find a domain sufficiently thin such that the mu k of the thin domain is close to the mu k of h. So finally, the two supremum are the same. So finally, if you want to compute this supremum, which was my aim, you need to compute this one, which is a much simpler problem because you are in 1D. So I already say that. So first of all, we prove that there exists an optimal H. Let's call it K star, which maximizes mu k of H among concave function in defined on 0, 1. Then I have to work a little bit to prove that, to be able to find the maximizer. And the maximizer is specifically what I plotted previously. For k greater than 2, the maximizer is a trapezoid. For k equals 1, it's a triangle, which gives exactly this value, because for this trapezoid, obviously the Sturm-Liouville problem can be solved You have something which is explicit. And so the main point is to be able to prove that the supremum is this particular shape. How do we proceed? So the concavity of H, so we use an analytic proof. Concavity of H tells you that H double prime is non-positive. And actually, in the sense of measure, H double prime is a measure. It's not necessarily a function. And what we want to do in the first step is to prove that it is a sum of Dirac mass. Because the sum of Dirac mass exactly corresponds to a polygonal line. And this use ideas developed in the last years by people like Jimmy Lambolet and so on, to be able to prove with an analytic reasoning that the fact that the support is discrete. Then we prove that the support is actually, you have only two possible points inside, and then we are able to conclude by an explicit computation. So let me skip the details. So this was for the supremum problem. If I am interested in the minimization problem, if I want to minimize mu k with a given diameter, what happens? For k equals 1, the result was already known. So the paper by Payne and Weinberger in the 60s. They prove the following inequality: mu1 is always greater than pi square over the diameter square. Moreover, this inequality is sharp, because if you take a sequence of rectangles, for which you know explicitly what is mu1, you can prove that this quantity converges to this one. So one more time, this is a sequence of collapsing domain, which is the infimum, and the infimum is pi square over diameter square. Okay, so for k equals 1, it's not really interesting. It is interesting, but it was already known. Let me mention that inequality is here also, of course, you need convexity in order to have this inequality, otherwise the inequality is not true. For the other mu k, actually the collapsing sequence is not good. And what I claim is that we have existence of a minimizer. We have existence of an optimal convex set when you want to minimize mu k with a fixed diameter. Why? So since you have a sequence of convex domain with a given diameter, you have only two possibilities by the Blaschke selection theorem. Either your sequence of convex domain converges to a convex body, something with a non-empty interior, and then it's easy to see that everything is continuous, the eigenvalues are continuous, and the limit will be a minimizer. Or your sequence of convex domain collapses to a segment. And so what we want to prove is the second part of the alternative cannot occur. So we want to rule out the second part of the alternative. And what is important is that when your sequence of convex domain collapses to a segment, of course you have the upper bound that I already mentioned, but you have a lower bound which is not so far actually, k square, pi square in that case. So if for this minimization problem, if you want to rule out the case where the sequence collapses, it suffices to find a domain, a particular one, for which you are below this lim-inf. It will mean that the collapsing domain are not the good competitors. And it's quite easy to do. Just take a square. I take the square. It's a tiling domain. So I can use the Polya inequality. Mu k of a square is less than the Weil asymptotic, which is 4 pi k here. If I multiply by diameter square, which is 2, I get 8 pi k. And the quantity I want to compare is k square, pi square, but it's okay, it works. For any k greater than 3, for k equals 2, you do not need Polya to make the explicit computation. So it proves that the square is better than any collapsing domain, so you have existence. Okay, you have existence, but what is a minimizer? So answer in some way. So these are numerical results. The minimizer from U2 is this set, which is a body of, it seems to be a body of constant width. This one is the disk, which is also a body of constant width. These two ones are not body of constant width, but what you can see is that the diameter constraint is saturated there and there. Here you have a flat part, meaning that the convexity constraint is saturated because it's flat. And the same here, you have diameter constraints. It's not a Rayleigh triangle. It's something with diameter constraint saturated there. And I think that you have flat parts here. It's not so easy to see. So this is from mu3, mu5. The two pictures from mu6, mu7. So from time to time you see the disk. So what we observe, but we are not able to prove it, it's exactly what I said, that the two constraints you have, one on the diameter, the other one on the convexity, seem to be saturated everywhere. Any point of the boundary saturates either one or the other constraint. And sometimes the minimizer seems to be a body of constant width. So in the last 5 minutes, let me report on the same problem with the perimeter constraint now. So for the perimeter, since the perimeter of convex set is always greater than twice the diameter, you get immediately this property with an optimal bound because you have to collapse like rectangles. But when k is greater than 2, for the same reason, this problem has a solution. You can rule out a sequence of convex domain which collapse. So your minimizing sequence of convex domain has to converge to a convex body, and this convex body will be the minimizer. Here also you can find a good competitor by using suitable rectangle. So I have no picture to show to you because I wanted to just finish with the maximization problem with the perimeter. So it's the same, it is the same way. You say, okay, my maximizing sequence now, either it converges to a segment or it converges to a convex body. You can eliminate the first case because you can find a domain, which is this rectangle, this particular rectangle, which gives a value which is greater than the upper bound we got previously. So this problem has always a solution. And let me finish with the case k equals 1. So when you are interested in maximizing perimeter square times mu1 in the plane, there was a conjecture which was not so by these guys, Rick Laugesen, Josip Polderovich, and Bartek Sudeja, where they say, okay, it seems that the maximizer could be the square or the equilateral triangle. It turns out that for the square and for the equilateral triangle, we are able to compute mu1. For the unit square, for example, mu1 is 1. Is pi square, sorry. mu1 is pi square. Perimeter is 4. So perimeter square times mu1 is 16 pi square. For the equilateral triangle, the unit equilateral triangle, mu1 is 16 pi square over 9. Perimeter is 3. So perimeter square times mu1 is also 16 pi square. So this value is obtained both by the square and the equilateral triangle. Is it by chance? Probably. And in particular, Bartek did some numerics and was not able to beat this value 16 pi square. So this is the reason of their conjecture. So this is an interesting conjecture because it's, to my knowledge, it's very rare that a shape optimization problem has two distinct solutions. Of course, there is a Mahler conjecture which has many solutions, but in spectral geometry in particular, I do not know any problem for which you have two distinct solutions. And it makes the problem very difficult because if you start with a convex domain and you say okay, I will just take as a test function the first eigenfunction of the square or the first eigenfunction of the equilateral triangle, okay, what is the good one? since you have two solutions, it's much more difficult. And so in a recent paper with Antoine Lemenant and Ilaria Lucardesi, we have been able to prove the conjecture, but only in a very specific case when you have two axes of symmetry. If the axes of symmetry are orthogonal, it's easy to prove that the square is better than any other convex. Easy. It's possible to prove that the square is better than any convex domain with two axes of symmetry, two orthogonal axes of symmetry. But you have also to deal with the third possibility of the axis of symmetry. But it is a way to separate the two candidates in two different classes and to make the problem tractable. Okay, so I stop here. Thank you.
Thank you, Professor Henrot. Any questions?
Yes, about the first result that you put for the second eigenvalue. If I go to general K, so for instance, for the test function, I can take a Voronoi diagram, but then where the argument is failed, I mean, where there is a major obstacle for moving up.
So let's say for mu3, for example,
yes.
First of all, the result is false. mu2 is not maximized by 3 bonds, but we have just numerical intuition for that.
Okay.
And it turns out that the maximizer we obtain numerically is not so far of 3 bonds. But the main point is that it's not absolutely not clear if we wanted to prove that what could be the test function. Now we have 3 points in the game.
But you cannot do like a Voronoi, some kind of Voronoi diagram? Or?
Yes, of course we can try to do it, but since we know from another point of view that the result is false, we didn't try a lot to prove that.
It's just numerically that you know.
Numerically, the result is false. The union of 3 balls is not the optimal domain. It seems to me that
it's close to this, or it's very far?
It's not so far. It seems to me, if I have a good memory of what I saw, it's something like that, which seems to be the best numerical domain for mu3. It's not so far, but it's not 3 balls. They get something. The guy who did some numerics, which has a greater eigenvalue than 3 balls.
So the difficulty would be in the starting point to find the test function with 3 points.
It would be one of the difficulty, but since we are convinced that the result is not true,
okay,
we didn't try.
Other questions? Yeah, please.
How about the Laplace equivalence?
You want to replace Laplace by?
Laplace optimal condition. Laplace operator.
Yes, of course. In that kind of problem, we need to have an operator which has a good symmetrical properties in order to be able to do something. If we replace Laplace operator by something quite general like divergence of C of x grad u, you can expect existence results. What is the domain which maximizes something? You cannot expect to have an description, analytic description of the optimal domain, except if you have just if you can come back to the Laplace operator. For example, if your operator is just minus a d2 over dx2 minus b d2 over dy2, it's more or less you can go back to the Laplace operator and get an ellipse, for example. But except in this simple case, I don't believe that we will be able to get an explicit description of the optimal domain.
Okay, thank you.
Yes?
Just a curiosity, but in this numerical computation of this canon, was it checked how far off it is from the Fourier? For this,
yes.
Could the Fourier equal?
So, no, we do not expect. We expect that for a given k, we are far. We are not at the Fourier bound. But when k goes to plus infinity, we go to the Fourier bound. So yes, here we are below, And all the numerical computation we have done confirm Polya conjecture, and it is just at the limit that we approach polyable.
Other questions? So if no more questions, let's thank Professor Henrot again. And we'll take a break and meet again at about 2:45.